Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Bridging Between Algebra and Calculus series and concerns the laws of logarithms. This guide describes the three laws of logarithms, gives examples of how to use them, and introduces a common application in which they are used to change an exponential curve into a straight line. Introduction. Logarithms are important tools in mathematics. They originally arose out of a need to simplify multiplication and division to the level of addition and subtraction. In the past, tables of logarithms were used to convert large numbers into logarithms. Then, by using the laws of logarithms detailed in this guide, multiplication was simplified to addition, and exponentiation, raising to a power, was simplified to multiplication. These days, calculators and computers can perform any arithmetical operation much faster than any human, and a working use of logarithm tables is no longer needed. However, logarithms are still an essential subject in algebra. For example, they are used to solve exponential equations, convert curves to straight lines, and, in calculus, the logarithmic function plays a fundamental role. In order to make the most of this guide, you should be familiar with the language which is used when describing logarithms. You should also be familiar with the logarithmic transformation and how this is used to solve exponential equations. If you are unsure about these topics, then the study guide, Basics of Logarithms, can help you. In this guide you will learn how to use the three laws of logarithms. Law 1. The logarithm of a multiplied by b equals the logarithm of a plus the logarithm of b. Law 2. The logarithm of a divided by b equals the logarithm of a minus the logarithm of b. Law 3. The logarithm of a to the power n equals n multiplied by the logarithm of a. In these laws, specific bases have not been defined, but the base you choose has to be the same in the mathematics on the left and the right of the equals sign. The first law of logarithms. The first law of logarithms relates multiplication to addition and states that the logarithm of a product of two terms a and b is the sum of the logarithms of those terms, so that the logarithm of a multiplied by b equals the logarithm of a plus the logarithm of b. This law is true for any base of logarithm, so long as you use the same base throughout a calculation. You could rewrite law 1 in base a as logarithm base lowercase a of capital A multiplied by b equals logarithm base lowercase a of capital A plus logarithm base lowercase a of b. You should remember that, because of the equals sign, this law also works from right to left, and so can be used to combine logarithms of the same base that are added together. When quoting this law, you should try to say it in full, as it is often misremembered as the log of a plus b. If you make the effort to quote it in full, then this very common error can be avoided. The logarithm of a multiplied by b is the logarithm of a plus the logarithm of b. There is no law of logarithms which relates the logarithm of a plus b. Example: rewrite the logarithm of 15 in terms of the logarithm of 3 and the logarithm of 5. As 15 equals 3 multiplied by 5, you can use law 1 with capital A equals 3 and b equals 5. So, for any base, the logarithm of 15 equals the logarithm of 3 multiplied by 5, which equals the logarithm of 3 plus the logarithm of 5. Example: express the natural logarithm of x plus the natural logarithm of 3 as a single logarithm. As the natural logarithm of x plus the natural logarithm of 3 is the sum of two logarithms, both in base e, natural logarithm, you can use law 1 to show that the natural logarithm of x plus the natural logarithm of 3 equals the natural logarithm of 3 multiplied by x, which equals the natural logarithm of 3x, where the answer has to also be a natural logarithm. The second law of logarithms. In the same way that Law 1 relates multiplication to addition, Law 2 relates division to subtraction. The law states that the logarithm of a quotient of two terms a and b is the logarithm of the numerator minus the logarithm of the denominator, so that the logarithm of a divided by b equals the logarithm of a minus the logarithm of b. Again, this law is true for a logarithm of any base lowercase a, like this. Similar to Law 1, the equal sign means that this law also works from right to left. When quoting this law, you should try to say it in full, as it is often misremembered as the logarithm of a minus b. If you make the effort to quote it in full, then this very common error can be avoided. The logarithm of a divided by b is the logarithm of a minus the logarithm of b. There is no law of logarithms which relates to the logarithm of a minus b or the logarithm of a divided by the logarithm of b. Example: express the logarithm of x divided by 4 in terms of the logarithm of x and the logarithm of 4. This is a logarithm of a fraction with a equals x and b equals 4, so you can use Law 2 to show that, for any base, the logarithm of x divided by 4 equals the logarithm of x minus the logarithm of 4. Example: simplify log to the base 3 of 18 minus log to the base 3 of 2. As log to the base 3 of 2 is subtracted from log to the base 3 of 18, you can use Law 2 with a equals 18 and b equals 2. Log to the base 3 of 18 minus log to the base 3 of 2 equals log to the base 3 of 18 divided by 2. As 18 divided by 2 is 9, this equals log to the base 3 of 9, and this in turn equals 2. The next section, or the logarithmic transformation, will explain why log to the base 3 of 9 equals 2. The third law of logarithms. The third law of logarithms relates exponentiation, raising to a power, to multiplication, and states that the logarithm of a raised to the power of n is n multiplied by the logarithm of a. The logarithm of a to the power n equals n multiplied by the logarithm of a. As with the other two laws, you need to use the same base throughout a calculation, like this. This law also works from right to left and can be used to change a number that is multiplied by a logarithm into exponentiation. Law 3 is often thought of as the most important because of this. It is especially useful when changing relationships described by curves into straight lines. The final section of this guide shows you how to change an exponential function into a straight line. Example: calculate log to the base 3 of 9. This may not seem like a question where you can use Law 3. However, as 9 equals 3 squared, you can use Law 3 with a equals 3 and n equals 2 to find that log to the base 3 of 9 equals log to the base 3 of 3 squared, which equals 2 multiplied by log to the base 3 of 3. And as log to the base 3 of 3 equals 1, see study guide Basics of Logarithms, log to the base 3 of 9 equals 2 multiplied by 1, which equals 2. This example can also be used to show that Law 3 is an extension of Law 1. You know that 9 can be written as 3 multiplied by 3, and so log to the base 3 of 9 equals log to the base 3 of 3 multiplied by 3. Now, applying Law 1 gives log to the base 3 of 3 multiplied by 3 equals log to the base 3 of 3 plus log to the base 3 of 3, which again is 2 log to the base 3 of 3. Example: express the logarithm of x plus 2 multiplied by the logarithm of y as a single logarithm. There is no rule that allows you to directly combine these two logarithms because of the coefficient of 2 in the second term. If you are unsure, look back at the precise form of Law 1. However, the second term, 2 multiplied by the logarithm of y, is in the form n multiplied by the logarithm of a, and so you can use law 3 with a equals y and n equals 2 to bring the coefficient inside the logarithm. The logarithm of x plus 2 multiplied by the logarithm of y equals the logarithm of x plus the logarithm of y squared. Now this is two logarithms added together, and so you can use law 1 with a equals x and b equals y squared. The logarithm of x plus the logarithm of y squared equals the logarithm of x multiplied by y squared. Example: evaluate 2 multiplied by the logarithm of 4 plus the logarithm of 8 plus the logarithm of 50. You cannot combine the logarithms with law 1 because of the multiple of 2 in the first term. However, you can use the third law, as in the previous example, to show that 2 multiplied by the logarithm of 4 plus the logarithm of 8 plus the logarithm of 50 equals the logarithm of 4 squared, which uses the third law, plus the logarithm of 8 plus the logarithm of 50, which equals the logarithm of 16, which is 4 squared, plus the logarithm of 8 plus the logarithm of 50, equals the logarithm of 16 multiplied by 8 multiplied by 50, which equals the logarithm of 6,400, where the third step uses law 1 twice. Changing exponential equations to straight lines. A very common use of logarithms in science and other disciplines is using them to transform curves into straight lines. This is particularly useful if you are studying exponential growth or decay. The equation y equals a multiplied by e to the power kx describes exponential behaviour and is extremely common in biology, chemistry, physics and economics. Usually a and k are constants, numbers, which describe properties of your system. A is the initial condition of the system, for example, initial population, and k is a factor which affects the curve. Positive k gives exponential growth, and negative k is exponential decay. The advantage of expressing a curve, such as an exponential function, as a straight line, is that you can determine the gradient and intercept of a straight line easily. See study guide, straight line. These properties are connected to a and k, which are difficult to determine from the curve itself. The following example gives the mathematics involved in using logarithms to change exponential graphs into straight lines, and also helps you to see the correct axes to use in your plot. Example: use logarithms to re-express y equals a multiplied by e to the power kx as a straight line graph. In order to be a straight line graph, a mathematical equation has to fit the pattern y equals mx plus c, where m is the gradient of the straight line and c is its intercept on the y-axis. The capital letters x and y are used to distinguish the variables from the lowercase y and lowercase x used in the exponential equation. To make y equals a multiplied by e to the kx fit this pattern, you first need to take logarithms. You would say taking logs of each side of the equation. This involves writing ln. As you have a base of e, it is wise to use natural logarithms in front of each side of the equation. So, the natural logarithm of y equals the natural logarithm of a multiplied by e to the kx. Now, using law 1 to make the right hand side into an addition. The logarithm of y equals the logarithm of a plus the logarithm of e to the power kx. Using law 3 on the second term of the right hand side, the logarithm of y equals the logarithm of a plus kx multiplied by the logarithm of e. Since the natural logarithm of e equals 1, the natural logarithm of y equals the natural logarithm of a plus k times x. Although this may not be immediately obvious, your equation now has the form of a straight line. You can see this by writing the two together, one above the other. The natural logarithm of y equals kx plus the natural logarithm of a above capital Y equals m multiplied by capital X plus c. Here the pieces of the equation line up in the same pattern where capital Y equals the natural logarithm of lowercase y, m equals k, capital X equals lowercase x, and c equals the logarithm of a. So, if you plot a graph with the natural logarithm of lowercase y on the vertical, capital Y, axis, and lowercase x on the horizontal, capital X, axis, you get a straight line with a gradient of k and a vertical intercept of the natural logarithm of a. So the constants a and k, which are difficult to calculate directly from the curve, can be found easily from the straight line. So, plotting your exponential graph, then plotting x against the logarithm of y, you get a straight line with an intercept of the natural logarithm of a and a gradient of k. Further guidance and information. If you have any further questions about logarithms or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor, or make an appointment to see a Learning Enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.